Okay, let's dive in. If you think about any modern electronic device you own, maybe your phone, your smartwatch, even the systems in your car, inside there are just countless tiny components: sensors, memory chips, controllers.
Right, all needing to talk to each other.
Exactly. And they need to do it fast, reliably, and critically using as few connections as possible. For decades, one of the main ways they've done this sort of miniature conversation, is using a protocol called I²C.
It really did become a backbone. I mean, its simplicity was key. Just two wires, clock, and data connecting multiple devices. Kind of the quiet workhorse inside everything.
A quiet workhorse, I like that. But, things have changed. The demands on our devices have just exploded. We're packing in more sensors, needing way longer battery life.
And faster responses, real-time stuff.
Precisely. And I²C, brilliant as it was, it started hitting some serious walls.
Yeah, limitations started showing up.
Which is exactly why the industry developed its successor, I²C. And based on the sources you shared with us, that's our mission today. We want to really understand I²C's legacy, figure out why those limitations push things forward, and break down what makes I²C such a significant step, maybe even revolutionary.
Definitely a major evolution. So we'll trace that journey, look at the fundamental electrical differences, which are quite interesting, explore all the clever new features I²C brings, and then see, where each one fits in today's electronics.
Perfect. So let's start right at the beginning. I²C, the veteran. It came out of Philips Semiconductor, now NXP, way back in, 1982?
That's right, 1982.
What was the core problem they were trying to crack back then?
The big headache was pins. Just the sheer number of pins and wires you needed to hook up chips on a board, especially simple peripherals like memory or I/O expanders talking to a processor.
Right. Before I²C, you had parallel buses, maybe other serial things.
Yeah, things that ate up valuable pin real estate on the chips and routing space on the board. I²C's goal was pretty straightforward. Create an efficient, low-speed, two-wire serial link. Cut down dramatically on those connections for chips on the same board.
Just two wires, SDA serial data and SCL serial clock. That simplicity must have been like a revelation for board designers.
Oh, absolutely. Fewer pins mean smaller chips, cheaper chips, simpler boards, lower-cost PCBs. It created this multi-drop bus idea.
Multi-drop meaning?
Meaning you could hang several different devices off those same two wires. You just use software addresses to choose which one you're talking to.
Okay, and the magic that let multiple devices share those lines without, frying each other electrically, that was this open drain signaling.
Yes, and understanding open drain is really key to understanding I²C. Its strengths, and eventually its weaknesses, too.
So how does it work?
With open drain, a device can only actively pull the line low for a logic. To get a logic 1, it just lets go. It releases the line.
The way to seize it.
Yeah, and an external pull-up resistor tied to the power supply is what actually pulls the voltage high for that one.
Ah, okay. So the resistor does the work of pulling high.
Right, and this creates what's called a wired AND behavior. If multiple devices try to pull low at the same time, it's fine. The line just goes low, no conflict. If they all release it, the resistor pulls it high. This is absolutely vital for sharing the bus, for things like arbitration, or letting a slower slave device hold the clock low, clock stretching.
Got it. But that passive pull-up, that sounds like where the speed limit comes in. It's not actively driven high.
Exactly. You nailed it. The line rises back to high isn't driven strongly. It depends entirely on how fast that pull-up resistor can charge up all the stray capacitance on the bus line.
And capacitance comes from?
More devices, longer traces on the board, even just less than perfect layout. All that adds capacitance. More capacitance means slower rise times.
And slower rise times mean you just can't clock the bus as fast.
Precisely. It puts a fundamental limit on the maximum reliable speed.
Okay. But despite that, I²C did get faster over the years, right? They kind of pushed that envelope.
They definitely did. It started off pretty slow, 100 kilobits per second. That was standard mode.
Right.
Then they managed fast mode at 400 kilobits. Then fast mode plus hit 1 megabit per second. And eventually high-speed mode, or HS mode, got up to 3.4 megabits.
But each step probably required more careful design, tuning those resistors, managing the capacitance.
Exactly. It became more sensitive as speeds increased. You had to really pay attention to the physical design.
And the error checking was pretty basic, too, just an ACK NAC after each byte.
Correct. Simple acknowledgement. The receiver pulls the data line low to say, ACK, got the byte okay, or leaves it high for an ACK, something was wrong.
So it tells you if the byte arrived, but not much about whether the data inside the byte was corrupted.
Not really, no. Very basic error indication.
And addressing. You mentioned software addresses, but they were static 7-bit or 10-bit addresses.
Yes, static, hard-coded into the chip, or maybe selectable with a couple of address pins.
What kind of problems did that cause as systems got more crowded?
Oh, that became a real headache, a major pain point. Imagine you need, say, 3 identical temperature sensors on the same bus.
Right.
They might only have 1 or 2 fixed address options. You'd have to make sure you could set them differently and ensure no other chip on that same bus segment happened to use one of those addresses.
To address collisions.
Collisions, yeah. It required really careful system-level planning, keeping track of every address used. Sometimes you even needed extra hardware, like bus multiplexers, just to isolate devices so you could reuse addresses.
And no standard way for the system to just figure out what was connected? Or for a new device to announce itself?
Nope. No plug-and-play discovery, no standard hot join mechanism. Very static.
Okay, so let's recap I²C's limitations. We have the speed limit from the open drain rise time and capacitance. We have the static addressing causing conflicts, basic error checking. What else started to really pinch, especially with, like you said, sensors exploding everywhere?
Yeah, that sensor proliferation was a huge driver. Think mobile phones, IoT, wearables. Suddenly you've got accelerometers, gyros, pressure sensors, light sensors, mics, you name it.
All needing to talk back.
Right. And I²C's 3.4 mark bits just wasn't fast enough for some of the high-resolution, high-speed sensor data streams. The capacitance limit meant you couldn't just hang, 20 sensors on one long bus easily.
Okay.
Multi-master scenarios, where you might have a couple of processors sharing peripherals, could still be tricky to manage reliably.
Right.
But maybe the single biggest issue, the one that really created a pin crisis, was how slaves signal they need attention.
The interrupt problem.
Exactly. An I²C slave device, like a sensor, it can't just raise its hand on the main I²C bus and say, hey, I've got data, or something happened.
It has no way to initiate.
No. So if a sensor detects a critical event or an ADC finishes a conversion, it needs a separate dedicated wire, a GPIO pin running from that slave all the way back to an interrupt input pin on the main processor.
Okay, so one extra wire per device that might need to interrupt.
Yes. Imagine a system with, say, 15 different sensors or peripherals that might need to signal the host. That's 15 extra signal lines on the PCB, 15 precious interrupt pins used up on your microcontroller or application processor.
Wow. Okay, that adds up incredibly fast.
Right.
Routing all that, plus the pin cost?
It's a massive burden. Complexity, board size cost, processor choice, it affects everything. The alternative is polling.
Where the master just constantly asks everyone.
Yeah, the host constantly goes around, sensor 1, got anything? Sensor 2, got anything? Sensor 3, over and over, which just wastes power and bus bandwidth. It's really inefficient.
So that need for dedicated interrupt lines, plus the speed limits, the power inefficiency of polling and pull-ups, the address headaches, it sounds like the stage was set for something new.
Definitely. It became clear that a more fundamental redesign was necessary to keep up.
And that brings us to I²C, the next generation. Developed not just by one company, but a collaboration.
That's right. The MIPI Alliance, specifically their sensor working group, really led the charge. This is around 2016, 2017. Key players like NXP, Qualcomm, Intel, and others were involved.
MIPI, they do a lot of mobile standards, right?
They do. Camera interfaces, display interfaces, so it makes sense they'd tackle the sensor interface problem. They sometimes called IC SenseWire initially, which kind of highlights that focus.
And their goals were pretty ambitious. Solve that pin crisis, get way higher speed and lower power, somehow stay compatible with the I²C world.
And add a bunch of advanced smart features.
Yeah.
Yeah, they wanted to bridge that gap between IC's simplicity and maybe the higher speeds of SPI, but with more intelligence.
So not just a faster I²C, but something that could potentially replace I²C and some SPI use cases.
That was definitely the vision, especially for sensors and control. And to help it get adopted widely, they created MIPI I²C Basic, a subset of the full spec, available royalty-free, covering the essentials. Lower barrier to entry.
Okay, let's really dig into the tech differences now. This is where we see how they tackled those I² problems. Signaling is a huge one. I² pure open drain. How does I² do it differently?
This is probably one of the cleverest parts. I² uses a hybrid approach. It dynamically changes how the lines are driven. Let's start with SCL, the clock line.
Okay.
In I²C, the master drives SCL push-pull. It actively drives it high and actively drives it low. No waiting for a resistor to pull it high.
So much faster, sharper clock edges.
Exactly. Essential for hitting those higher frequencies. Now, SDA, the data line, is even more interesting.
That's the really hybrid part.
Yeah. SDA actually starts in open drain mode.
Why?
Two main reasons. First, backward compatibility.
Yeah.
It needs to look like I²C initially to allow mixed buses. Second, I²C itself uses open drain signaling for critical things like bus arbitration and its own in-band interrupts, which we'll get to.
Okay, so it starts open drain.
But here's the trick. Once the master knows it's talking to an IC device and any arbitration is finished, the SDA line switches to push-pull mode just for the data transfer part of the message.
Ah, so it actively drives the data bits high and low during the main transfer.
Precisely. Actively driven data means much faster transitions than relying on that passive pull-up resistor. That's a huge part of how I²C achieves higher data rates.
That dynamic switching is really neat. What about power consumption? I²C's pull-ups draw static current, right? Especially if you need stronger ones for faster modes.
Power efficiency was a massive design goal for I²C, especially thinking about battery life in mobile and IoT. First off, it's designed for lower operating voltages.
Lower voltage means less power.
A lot less. Power is proportional to voltage squared, remember. So I²C typically runs at 1.8V, 1.2V, even down to 1.0V with I² Basic, compared to older 5V or 3.3V I² systems. That voltage drop alone is a huge power saving.
Okay, P proportional to V squared. Got it.
Then, combine that lower voltage with the much faster speeds transactions finish quicker, so the chips can go back to sleep sooner.
Less time active.
Right. And then add in the fact that you don't need strong pull-ups all the time, and you eliminate all that power wasted on pulling because you have in-band interrupts.
Okay.
Put it all together, and I² is dramatically more energy efficient. The numbers are pretty staggering, so only like 5 to 18 times less energy used per kilobyte of data transferred compared to I²C.
Wow, 5 to 18 times. That stat alone just screams mobile wearables.
Absolutely. It's a game changer for anything running on a battery.
Now, capacitance. You said that was I²C's speed limiter. How does I² handle that? Needing much faster signals. Does it just tolerate less capacitance?
Much less, yes.
Yeah.
I²C could often handle maybe 400, sometimes up to 550 picofarads of total bus capacitance. I²C, because it relies on those fast, clean, actively driven edges, needs a much cleaner signal path.
Is it stricter?
Much stricter. The typical limit for high-speed I² operation is often down around 50 PF. That's a big difference.
50 PF versus 400 or 500 PF, okay? What does that mean practically for designing a board?
It means your I² bus segments generally need to be shorter. You can connect fewer devices directly onto a single run before hitting that capacitance limit. Careful PCB layout becomes much more critical, minimizing trace lengths, avoiding stubs, controlling impedance maybe.
So more complex layouts, potentially?
Or, very commonly, it means using I² bus switches or hubs. These devices let you segment the bus. You can have short, low capacitance sections running at high speed, connecting back through the switch. It's a way to manage that capacitance budget in larger systems.
Makes sense. Manage the physical layer to maintain the performance. Okay, so beyond the electrical signaling, what about the protocol itself, the big advancements? Speed is obvious. I² starts faster even in its standard mode.
Yes, the baseline is called I²SDR, Standard Data Rate. That runs with an SCL clock up to 12.5 megahertz, which gives you an effective data rate around 11.1 megabits per second.
Which is already much faster than I²'s best.
Oh yeah, way faster than 3.4 millibits. And SDR still uses a structure that looks a bit like I²C messages, 8 data bits plus a 9th bit. But that 9th bit gets repurposed in I² for parity or flow control.
Okay. And then you mentioned HDR modes, high data rate, for even more speed.
Exactly. These are optional modes you can switch into using specific commands, called Common Command Codes, or CCCs.
What kind of speeds are we talking with HDR?
Well, there's HDR DDR, double data rate. It transfers data on both the rising and falling edges of the clock, so roughly double the SDR speed, getting you up towards 25 millibeats.
Okay, using both clock edges. Clever.
Then it gets even more interesting with ternary modes.
Ternary, like 3 levels, not just 0 and 1.
Exactly. Instead of just 2 voltage levels for binary 0 and 1, these modes use 3 distinct voltage levels on the data line. This lets you encode more information per clock cycle.
Huh. How does that work out?
There's HDR TSP ternary symbol pure. Uses ternary on both SDA and SCL. They get you the highest single-lane speed, around 33.3 millibps. But the catch is, it only works on a pure IZ bus. No legacy IC devices allowed.
Right.
Then there's HDR TSL ternary symbol legacy. It uses ternary just on SDA, keeping the SCL clock conventional. This one can potentially work on a mixed bus with IC slaves, but those slaves need to have those spike filters we'll talk about later.
Okay, so different flavors of HDR for different bus setups.
Right. And for really high throughput needs, like maybe bulk data transfers, there's even HDRBT, bulk transport mode. It can use multiple data lanes to push speeds way up, potentially towards 100 Mbps or more.
Wow. Okay, so with speeds like that, I²C isn't just for setting configuration registers anymore. It can handle serious data streaming.
Absolutely. It makes it versatile enough to potentially replace not just I²C, but also some applications where you might previously have needed SPI for the speed.
Got it. Now, another huge change you mentioned, dynamic address assignment, DAA. This sounds like it solves that whole static address conflict nightmare in I²C.
It really does. It's a game changer for system management. No more manually mapping addresses and hoping there are no clashes.
So how does it work? What happens at startup?
When the system powers up, the I² master controller initiates the DAA process. It sends out a special broadcast command, basically asking, okay, who's out there?
And the I² slaves respond.
Yes. Each I² slave device on the bus has a unique, factory-programmed 48-bit identifier called a provisional ID, or PID. They also report their basic capabilities. The master uses this information, going through a defined sequence, to assign a unique 7-bit dynamic address to each I² device it finds on the bus.
So the system literally discovers the devices and gives them temporary addresses for that session.
Exactly. On the fly, it automatically resolves any potential conflicts because the master ensures that each assigned dynamic address is unique on that bus segment. Its discovery and configuration baked right into the protocol.
That must simplify system design enormously.
Hugely. Especially if you have multiple identical sensors. And critically, that assigned dynamic address isn't just for talking to the device, it's also used to set the priority for.
The in-band interrupts.
Precisely. Let's talk about in-band interrupts, or IBI. This is probably the single biggest feature addressing that pin crisis we talked about with I²C.
This is how they got rid of all those extra interrupt wires.
Yes. It's incredibly elegant. An I² slave device that needs the master's attention, maybe it has new data, or an event occurred, doesn't need a separate pin.
So what does it do?
When the bus is idle, SCL and SDA are both high, the slave wanting to interrupt simply pulls the SDA line low, just the data line.
Kind of like initiating a start condition, but without the clock involved initially.
Exactly. The master sees SDA go low while SCL is high, which is a unique condition outside of normal data transfer. It recognizes this as an interrupt request.
On the same two wires used for everything else. That is clever.
It really is. So the master acknowledges the interrupt request. Then the interrupting slave transmits its 7-bit dynamic address, the one assigned during DAA.
So the master immediately knows who interrupted.
Yes. And if by chance multiple slaves try to interrupt at the exact same time,
What happens then?
they use their dynamic addresses for arbitration, right there on the SDA line. The slave with the lowest dynamic address wins the arbitration.
So lower address means higher priority interrupt.
Exactly. Priority is built in based on the DAA assignment. The winning slave then gets acknowledged and can often send a single byte immediately, a mandatory data byte, to give the master quick status info.
And the result is no more dedicated interrupt pins needed.
Correct. 0 extra pins per slave for interrupts. Think of the savings. Pins on the processor, routing complexity on the PCB, board space. It's a massive system-level advantage. And lower power, too, because the master doesn't need to pull anymore. It just waits for an IBI.
That really is a fundamental shift from I²C. What other cool things can I² do that I² just couldn't?
Well, building on DAA, there's hot join capability.
Meaning devices can connect while the system is running.
Yes. An I² device can be physically connected to an already active bus. It signals its presence by issuing a start condition, followed by a special reserved address known as the hot join address.
The master sees that special address.
Recognizes it as a hot join request, and then initiates a DAA cycle just for that newly connected device, integrating it onto the bus without disrupting the others or needing a full system reset.
Okay, that's useful for modular systems, maybe, or devices that power down completely and need to rejoin.
Exactly. Plug-and-play modules, dynamic power management scenarios. It adds a lot of flexibility.
Any other key features?
There's also built-in support for time control, including timestamping.
Timestamping data on the bus. Why is that important?
Think about sensor fusion. You're combining data from maybe an accelerometer, a gyro, a magnetometer, to figure out orientation.
Right. You need to know they were sampled at the same time or know the time difference.
Precisely.
Yeah.
With I²C, a sensor can capture a timestamp at the moment it takes the reading and send that timestamp along with the data. This is much more accurate than the master trying to guess when the data was captured based on when it arrived over the bus. It reduces latency and jitter in time-critical sensor applications.
Better data correlation.
Much better. And finally, I should mention the Common Command Codes, or CCCs. These are standardized broadcast or direct commands defined in the spec for bus-wide operations,
Great.
like initiating DAA, entering or exiting HDR modes, managing power states, resetting devices, querying capabilities. It provides a standard way to manage the bus and the devices on it.
Okay, so I²C is packed with features: faster speeds, dynamic addressing, in-band interrupts, hot join, timestamping, standard commands. It really addresses all those I² weak spots. But what about that backward compatibility goal? Can I² masters actually talk to old I² slaves on the same bus?
Yes, they are designed to. That was a core requirement. An I² master controller can detect when it's addressing a legacy I² slave based on its static address falling outside the dynamic range.
And then it adjusts?
It adjusts. It slows down to the appropriate I² speed, like 100 kilohertz or 400 kilohertz, uses the standard I² open drain signaling for that transaction, respects clock stretching, and handles the basic ACK and ACK. It essentially speaks plain old I²CK when talking to an I² device.
Okay, that sounds good. But is there a catch for the poor old I² slave sitting on a bus where the master might suddenly start talking I² super fast to another device?
Yes, there is one main requirement for the I² slave if it's going to coexist reliably on a mixed bus. It must have what's called a 50 nanosecond spike filter on its SDA and SCL inputs.
A 50N spike filter, what does that do?
Remember how fast the I² signals can be, especially the clock edges in push-pull mode? To an older I² device without this filter, those fast transitions might just look like noise or glitches.
It might misinterpret them.
Exactly. It could see false start or desktop P conditions or extra clock pulses, potentially messing up its internal state machine. The 50-on spike filter tells the I²C device, ignore any pulse on the line that's shorter than 50 nanoseconds. It effectively filters out the fast I² traffic that isn't intended for it.
So most modern I² devices probably include this, but older ones might not.
That's generally the case. You have to check the datasheet for the specific I²C part if you're planning a mixed bus. If it doesn't have the filter, it might not behave reliably when I² traffic is present.
And on these mixed buses, you still need the external pull-up resistors for the I²C parts.
Typically, yes. Even though the I² master uses push-pull, and I² slaves might have weak internal pull-ups, the legacy I² slaves still rely on those external resistors to get their logic high level.
But the biggest challenge on a mixed bus, you said earlier, comes back to capacitance, trying to keep it below that strict 50 PF limit for the I² devices.
That's usually the main hurdle, yes. Every device you add, I² or I²C, adds some capacitance. Since I²C devices often have higher pin capacitance, adding even a few of them can quickly push you over the 50 PF limit needed for the I² parts to run at their highest speeds.
So how do designers handle that in practice?
Often, it forces bus segmentation. You use an IC to IC bridge chip or an IC bus switch. You put the high-speed IC devices on one low-capacitance segment connected directly to the master, or through a switch. Then you put the legacy IC devices on a separate segment connected via the bridge or switch.
So the master talks IC at high speed on one side, and the bridge translates to slower IC on the other side.
Exactly. It isolates the capacitance, allowing both types of devices to operate correctly, but adds the cost and complexity of the bridge chip.
Okay. So migrating from IC isn't just a chip swap. It's choosing the right IC masters and slaves, carefully managing the layout for capacitance, potentially adding bridges.
And writing more complex software drivers. You need to handle DAA, manage the CCCs, service in-band interrupts, potentially switch HDR modes. It's definitely more involved than basic IC.
But the payoff is in those system-level benefits.
Right. The pin savings, the power reduction, the performance boost, the dynamic features. For complex systems, especially mobile, IoT, automotive, that upfront effort is often well worth it.
Let's talk about where we actually see these protocols in the wild today. Where is I²C still king?
Oh, I²C is still everywhere and isn't going away anytime soon. For simple, cost-sensitive tasks, it's just fine. It's perfect.
Like what kind of tasks?
You find it connecting to basic temperature sensors, real-time clock chips, small configuration EEPROMs where you just read or write a little bit of data occasionally, simple command and control for things like LED drivers or fan controllers. Power management buses like SMBus and PMBus are often based on I²C. Monitor control using DDC, it's the go-to for basic, low-speed configuration and control. Cheap, mature, widely understood.
Makes sense. So where is IC gaining ground? Where is it emerging?
IC is really taking hold in applications where those I²C limitations become serious problems. The absolute prime example is mobile.
Smartphones, wearables.
Exactly. Smartphones, tablets, smartwatches, they are the perfect storm for I²C. They're jam-packed with sensors. They desperately need to save pins because space is tight, so IBI is a lifesaver. Power consumption is absolutely critical for battery life, and they need to handle sensor data quickly for things like motion tracking, image stabilization, context awareness.
It seems tailor-made for mobile.
It really was driven initially by mobile needs, but it's definitely expanding beyond that now.
Where else?
You're seeing it more in other IoT devices for the same reason: sensors, power, maybe needing faster data. Sensor hubs and sensor fusion processors are a natural fit. They need the speed and time stamping to combine data effectively. Automotive is another growing area with more and more sensors in cars. Even enterprise systems like servers are starting to use it for management tasks, and as part of newer memory standards like DDR5 for communicating with memory module components. SSDs, potentially medical devices, industrial automation.
Basically, anywhere you have high sensor counts, tight power budgets, a need to reduce connections, or require dynamic configuration and higher speeds.
That sums it up well. Anywhere performance, power, pin count, and intelligent management are pushing beyond what I²C can comfortably deliver.
Okay, so just to quickly recap the main trade-offs one last time. I²C. Simple, mature, cheap, more forgiving on capacitance.
But limited speed, less power efficient, needs those extra interrupt lines. Static addresses cause headaches. Very basic error checks.
And I²C. Huge leap in speed and power efficiency, gets rid of interrupt pins via IBI, solves address conflicts with DAA, enables hot join, has robust error handling, timestamping, standard commands.
But more complex protocol, potentially higher initial costs for components and development, requires very careful layout to manage that strict capacitance limit. And mixing with legacy I²C needs those spike filters and often segmentation.
So looking at the big picture, IMAC is still the solid workhorse for simpler, cost-driven jobs. It's not disappearing.
Not at all. It'll be around for a long time for those roles.
But I²C is really emerging as the essential forward-looking standard for modern complex systems. The ones demanding that high performance, low power, and smarter ways to handle lots of peripherals.
That's exactly how I see it. It was designed specifically to overcome I²C's hurdles and meet the needs of today's and tomorrow's devices.
The choice really boils down to the application's specific needs. Simple control. I²C might be fine. High-speed sensors, lots of interrupts, battery power critical. I² becomes very compelling.
And remember, mixed buses are a viable migration path, but you have to design for it carefully, especially around capacitance and compatibility. I²C's true value isn't just one feature, it's the whole package of improvements working together: speed, power, pins via IBI, DAA, reliability. It's an evolution in how chips communicate on the board.
This has been a great deep dive using the materials you shared. It really maps out that journey from I²C's simple, robust origins to I²C, well, much more sophisticated, feature-packed standard. It's clearly a path driven by the relentless demands of modern electronics. More speed, less power, smarter interaction.
It really is fascinating to see how they managed to integrate so much intelligence and functionality like interrupts and dynamic addressing onto just those two wires, transforming the bus.
Yeah, it makes you appreciate the intricate conversations happening inside the devices you use every day.
Absolutely. And, thinking about how I²C absorbed functions that used to need dedicated pins, like those interrupts, consolidating them onto the shared bus through clever protocol design, it does make you wonder.
Wonder what?
Well, it raises an interesting question for the future, doesn't it? What other traditional dedicated hardware connections in embedded systems might be the next targets for a similar kind of two-wire consolidation using smart protocols to simplify hardware even further?
That's a really interesting thought to leave our listeners with. What else could be folded into an intelligent two-wire bus? Food for thought. Thank you again for sharing the sources that made this deep dive possible today.